Ever wonder how your phone miraculously streams high-definition video while you're buried deep inside the concrete bunker of a massive building? Well, welcome to this explainer. Today we're going to dive right into a crucial yet entirely hidden world that's humming away just behind the drywall and ceiling tiles of your everyday life. We are demystifying cellular coverage by exploring indoor building solutions, or IBS. We're going to look at exactly how this hidden magic actually works.
Here's our roadmap for today's explainer. We'll start with the need for IBS, then move into signal distribution, followed by antennas and hardware, then the site survey, and finally, the detailed design. Let's get into it.
Section 1. The need for IBS. Breaking through the concrete.
Okay, so it's an incredibly relatable question, right? Why do our phones suddenly drop a call or completely lose signal the exact moment we step inside a hospital, a giant shopping mall, or even just a modern office building? Well, the reality is that modern building materials, we're talking tinted glass, heavy steel, non-reinforced concrete, and complex internal partitions, they act as massive shields. They literally block those outdoor radio frequencies from getting inside. To combat this massive barrier, engineers use indoor building solutions. Enter IBS, our hero's solution. It's a dedicated internal system specifically engineered to provide seamless indoor coverage. It completely bypasses those pesky obstacles of outdoor macro cell towers, ensuring excellent coverage, massive capacity, and high quality for every single subscriber walking around inside a building. Now, there are 5 major technical drivers pushing the telecom world to heavily adopt IBS. First, just the basic demand for continuous coverage. We all expect our phones to work everywhere now, no excuses. Second, indoor activities actually generate incredibly high traffic. People are streaming, working, and calling from inside all day long. Third, like we just talked about, there is terrible indoor penetration from outdoor macro sites. Fourth, and this is a big one, we actually need to offload those outdoor cells. If everyone inside a 50-story skyscraper connects to the outdoor tower, that tower gets completely overwhelmed. And finally, by balancing that load, IBS vastly improves the overall network performance for everyone. These authentic, handwritten engineering notes straight from our source material really show how foundational these core demands are. You can literally see these 5 drivers listed out by an actual radio frequency engineer. It just validates how critical these challenges are in the field today. And the scale we're talking about here, it is absolutely immense. The target environments for IBS are incredibly diverse. We're talking office complexes, sprawling shopping malls, hotels, restaurants, hospitals, where, let's be honest, connectivity can literally be a matter of life and death. Plus, VIP guest houses, huge exhibition centers, highly secure government buildings, and sprawling transit hubs like airports and railway stations. Every single one of these unique architectural environments requires a heavily customized IBS network.
Section 2. Signal distribution. Managing the flow. So, the absolutely crucial point here is understanding how we divide the signal. Think of this a bit like a plumbing system, okay? The cellular signal is your water pressure. A splitter divides that signal evenly. A two-way splitter results in about a 3.25 decibel loss, while a three-way splitter has a slightly higher 5.5 decibel loss. A coupler, on the other hand, is a bit different. It offsets cable losses over long distances with an uneven split. So a 7 dB coupler pulls off 7 decibels of power for a nearby antenna, while losing only 1.5 decibels on the main line. Similarly, a 15 dB coupler pulls off 15 decibels but loses a tiny 0.3 decibels on the pass-through. It's all about perfectly balancing the pressure. Now, depending on the medium they are working with, engineers rely on a few different types of splitters. Coaxial cable splitters are your standard broadband internet dividers. Optical splitters are used heavily in fiber optic telecommunications. DSL splitters, those separate voice from digital data so you don't get interference. Hybrid splitters, which are pretty cool, can handle both optical and electrical signals at the same time. And of course, standard telephone line splitters just divide a single line into multiple extensions. Section 3. Antennas and hardware. Reaching the user. This brings us to the actual endpoints, the antennas. Engineers carefully choose these based on the spatial layout of the room. An omni antenna, for example, broadcasts in a full 360-degree circle with a low gain of 2 dBi. That's absolutely perfect for the dead center of a big open room. A flat patch omni gives a slightly stronger 5 dBi boost. But what if you have a really long, narrow corridor? Well, then you'd use a panel antenna. It's directional, pushing a focused 90-degree horizontal by 90-degree vertical beam with a much stronger 7 dBi gain. Most modern antennas also feature MIMO. That stands for multiple input, multiple output. Basically, it means they can concurrently handle multiple frequency bands and generations of data streams all at the exact same time. It's like a multi-lane highway for data. They are pushing 2G at 850 and 1900 megahertz, 3G adding in that 2100 band, and 4G spanning everything from 700 all the way up to 2600 megahertz simultaneously. But what about areas where capacity needs are pretty low, but the signal is just incredibly weak? In those cases, engineers will deploy repeaters instead of building out a full base station. Repeaters simply grab a weak signal, amplify it, and push it back out. A band-selective repeater amplifies an entire specific frequency band, whereas a frequency-selective repeater is way more precise. It only grabs and boosts 2 or 3 very specific frequencies. To round out our hardware catalog, we have combiners. These allow multiple transmitters to feed into a single antenna. A hybrid combiner doing this typically introduces about a 3 decibel loss. And to tie this whole shebang together, we rely on trunk amplifiers to boost the signal on super long runs, massive feeder cables to carry the main signal through the building, and smaller jumper cables to make those final, precise connections to the equipment. Okay, so we've got a solid understanding of the hardware arsenal, right? The splitters, the couplers, the antennas, but you can't just walk into a building and start bolting this stuff to the ceiling. How do we actually map out and design the network to ensure absolutely perfect coverage?
Section 4. Site Survey. Mapping the environment.
The whole workflow kicks off with site acquisition. Step 1 is the customer request. Let's say a hospital realizes their doctors are missing critical pages because of dead zones in the basement. Step 2 is a preliminary site survey if they already know the specific target building, or an area survey if they are just targeting a general zone. Once the initial feasibility is all laid out, Step 3 is securing formal customer approval to actually proceed with the build.
Next, we enter the intelligence gathering or pre-planning phase. This is where engineers collect deeply detailed building information, stuff like architectural floor plans and what materials the walls are made of. They also look at the surrounding outdoor network information to understand what kind of signal interference might be leaking inside. From there, they draft up an initial solution design and calculate a budgetary cost estimation, so the client knows exactly what kind of financial commitment we're talking about.
Once that budget is approved, it's time for boots on the ground, the full site survey. Engineers literally walk the entire building, physically measuring radio frequency propagation. They map out the final exact locations for the base transceiver station, the BTS, and every single antenna. They figure out the exact final cable routing through the drop ceilings and elevator shafts, and they take comprehensive photographic documentation of all these spots to act as a guide for the installation crew.
Section 5. Detailed design. The final blueprint. All that footwork leads right here. The detailed design report. It includes a highly technical system diagram, often called a trunking diagram, showing how every single hardware component connects. It includes this seriously math-heavy power budget calculation. That math basically proves that after every single splitter drop and cable loss, enough signal still remains with the final antenna to actually reach your phone. It features a solution description template, and finally, the Technical Site Survey Report, or TSSR. This document serves as the ultimate blueprint for the installation teams. Circling back to our source material one last time, you can really see how these exact concepts are meticulously planned out on paper first. We've got the target buildings listed right at the top, the precise decibel losses calculated for the splitters, the unequal power distribution plan for the couplers, and the varied dBi gains mapped out for the omni and panel antennas. It just brilliantly summarizes the precise, invisible math that dictates our indoor connectivity.
So I want to leave you with this final thought. Next time you are waiting in a subterranean subway station, or you're walking through a massive shopping mall and you look down and notice you have perfect 4G or 5G coverage, will you look up at the ceiling and think about the complex web of splitters, couplers, antennas, and meticulous power budgets making it all possible? Thank you so much for joining me on this explainer. I really hope this gave you a brand new appreciation for the hidden engineering happening all around us. Keep learning, and I'll catch you next time.